So starting in chapter 6, we'll be taking a look at rational expressions. And that word rational, if you're not familiar with that word, that denotes dealing with a fraction. And so these rational expressions, as it says here, are obtained by dividing one polynomial by another. So we're going to see these fractions where there could be polynomials or multiple terms in both the numerator and denominator. And so the first thing we want to learn how to do is simplify them, just like with regular fractions. Think of it as reducing a fraction. You're looking for those common factors, like when you would see 4/6 and know it reduces to 2/3. Now, here is a very important idea, very critical to work on understanding this and not making this mistake throughout this chapter and beyond. I summarize it in this mixed trick of saying never cancel pieces. You could also call that never cancel terms, because the idea is we only cancel factors. The only way we're going to be canceling or reducing these rational expressions is when they have common factors. So what that means is, as we look at some examples here, if we're going to reduce or simplify them, like the very first example, we don't want to start looking at things like, hey, there's r's in both, let's cancel those, or hey, look, the 20 and the 12 can reduce, or any other piece of a numerator and denominator, or piece of an expression, right? We're not going to cancel individual terms or reduce them. To see them as factors, that's essentially what we need to do. We need to factor them and then look for factors that cancel. So again, rather than drawing lines through pieces here, always first and foremost see what these things factor to. So in this case, this fraction, the numerator, 5r minus 20, our first factoring technique is GCF, and so I'll always try that first. And in this case, there's a GCF of a 5 in common with those two terms, leaving me r minus 4 left over. Second expression, the denominator, I see a GCF of a 3. And I factor that out, I see an r minus 4 left over. Now that these things are factored, as in something times something, and here something times something, common factors are allowed to cancel, so those pieces, now again I call them pieces, but they are factors of the numerator and denominator. They match and they cancel, meaning this rational expression reduces down to 5/3. But we weren't allowed to cancel until we saw the factors in common. Now, to make sure we understand that idea, looking at the next example, we see a 3 in both. And in fact, 3 is the only thing down here. And so in a sense, 3 is a factor down here. You could think of it as 3 times 1 if you really wanted to. But up here, this 3 is only part of a term. And if I look at 3x plus 7, there's nothing I can do to factor that, right? There's no GCF or any other approach. So this really is not factorable, which means I'd have to think of 3x plus 7 as a whole thing, as one factor, as a group. And so in that sense, these 3's, even though you see 3 times x and 3 times 1, these are not going to cancel. 3 is not a factor of the numerator, it's just a factor of that term. And that's what we don't want to cancel. So in that case, we would just say that is already reduced. There's nothing to do there, nothing to simplify. All right, for the third example, same thing. Don't be tempted to cross out y squareds. Don't be tempted to cancel out 2 and 14. We want to factor these things, which we know how to. These are both easy cases. So we're looking at the binomial here, two binomials, numbers that multiply to negative 14 and add to negative 5. I'm going to probably stop doing the numbering off to the side unless it's more involved numbers. Feel free to keep doing that in your work though. We need numbers to multiply to negative 14 and add to negative 5. Well, that would be a negative 7 and a positive 2. Now down here, for this other easy case, we're looking for numbers that multiply to a negative 2, but add to a positive 1. That'd be a positive 2 and a negative 1. And now that they're factored, we can see those factors are identical and will cancel, and we're left with y minus 7 on top over y minus 1 in the denominator. And that's it. Okay, now, a little bit of a trick here to notice when something might reduce, or is reducible, and it might not look like it. Here's x minus 7 over 7 minus x. Now, the question of, are they the same factor? No, they are not, right? One is a positive x, one is a negative x. That's not, those are not matching. The question of can they be is this little bit of what I call the negative trick in these factoring type problems. If we notice that they have the same terms, but in both cases the opposite sign, meaning this is positive x and this is negative x. Here we got a negative 7, and that's a positive 7. This is a very specific situation, it's summed up right there, where you can then look at either the numerator or the denominator, doesn't matter which one, and say, well, what would happen if I factored out a negative 1? So if I leave this numerator as x minus 7, but on the denominator, I say, what if we factored out a negative sign, like a negative 1? That would change positive 7 to negative 7, and change minus x to plus x, right? But now, that, if I just reorder it, put the x first and the negative 7 second, that says x minus 7. And what we want to point out is what I mentioned earlier. Up here, x minus 7 doesn't actually factor, but you can think of it as a whole thing as a factor. Again, like it's times 1, if that helps you, right? This whole thing times 1 makes it a factor up top. There's a factor of it on bottom, which allows those two to cancel. And now if they've canceled completely, just like any other fraction, that's a 1 over a 1, although we have a negative. So we have a positive over a negative. So we had to have a negative 1 that this would actually reduce to using that bit of a negative trick there. Now, the negative trick isn't just something we can always do. It's a very specific situation. So just to run through quickly here and point out which of these would work and which one wouldn't. This example is one we just saw, right? We got a positive x, negative 7, positive 7, so that's a place the trick would work. Here, notice we see a difference in sign in here, but if you compare terms, they're both positive x's. Now, yes, there's a positive and a negative 7, but that doesn't matter. If we don't have both terms opposite signs, then factoring out that negative is just going to make these signs match and those be opposite. So that's not the right scenario. Same thing here. You see a plus and a minus 7, those are opposite, but we have both x's, again, are the same sign, so not going to work there. This last example, though, positive x and negative 7 and positive 7, this would be another situation where you could factor a negative out of either one and then end up with similar factors that would cancel. So there's specific situations where that negative trick can come in handy, so just watch for that. Now that we know how to reduce a fraction, we want to look at two related operations, which are multiplication and division of these rational expressions. And it starts off much like the simplifying did. We want to see the factors that make up all of the numerators and denominators, and then cancel the things we can. Now notice here we're talking about multiplication, and with multiplication, just like with fractions, you would want to cancel any common factors between a numerator and a denominator, whether they're in the same fraction or whether they're across from each other, right? And then we can combine into one fraction, and this specifically mentions leave in factored form. There's no real benefit to multiplying it back out necessarily as in terms of a final answer. So the very first example we've got here is already factored for us. Everything's been broken down, so all we have to do is say, I see an x plus 2 in a numerator there, and an x plus 2 in a denominator there. I see an x plus 3 in the denominator there, and in the numerator there, and an x plus 1 there and there. So any common factor between a numerator and a denominator will cancel, and in this case, that's just leaving us x plus 4 over x minus 2, and that's it. That is our fully reduced final answer there. Now, what happens when we have to do some of the work ourselves? Let's take a look at this first one here. So 16 minus x squared, if we can factor that as a difference of squares. 4 squared is 16, and x squared is x squared. So 4 plus x times 4 minus x. The order is important, right? If 16 was our a, then the 4's have to be our a's. That's very crucial here. That's 2x on the denominator. It's a single term that doesn't factor, although notice 2x does mean 2 times x. Just make sure we keep that in mind. Same with 4x squared. Doesn't factor, but we have the factor of 4 and the factor of x squared. And then this is another easy case, trinomial, where we want numbers that multiply to negative 4 and add to negative 2. So that would be a negative 4 and a positive 2. Now, as far as what we can do to cancel or reduce here, let's start with some of the things that are already in the right form, like the number 2 and the number 4. Right? These are in themselves factors. So this is not canceling terms like I mentioned earlier. This is a factor of 2 and a factor of 4 that can cancel or reduce to 1 to 2. Similarly, this x and this x squared. Now x squared means you've got two x's multiplied together up here, so this x can take out one of those x's. Right? Those are factors of x. Now, looking at the binomials, none of them match perfectly. However, here we have a 4 minus x, here we have an x minus 4, right? Positive and negative 4, positive and negative x. That's a situation where you can use a negative trick. So, however you want to notate it, I'm going to just put it right below and say that x minus 4 is the same as the negative of negative x plus 4, right? Factoring the negative out of that binomial there, that factor. But now I've got a positive 4 and a negative x, so now those cancel. So I turned that into that, but now those have canceled. So up top, we have this 4 plus x, we also have that 2, and we have a single x left over. So 2 and an x and a 4 plus x, all left in the numerator. Now in the denominator, that canceled, that turned into that which canceled. There's still a negative, right, like a negative 1 down here, and that x plus 2, so something like that. And although that's a decent form, generally speaking, we don't leave a negative sign like that in the denominator. We can move it out front and just say this is negative of 2x times 4 plus x over x plus 2. That's just the cleaner, better way to write that final answer. And again, you could distribute the 2x if you wanted to have another form of this final answer, but factored form really tells the story. And so, now that we understand multiplication, to look at division, all we have to remember is our rule that when dividing by a fraction, we change it to multiplying by the reciprocal, and that exact same rule will apply to these problems as well. Notice for division, I always say, take the time to rewrite it first and then factor, just so you're not tempted to cancel factors in this form. We don't want to cancel in the division form. So the first thing I do is I take the time to rewrite the problem. My first fraction times my second fraction's reciprocal, right? I gotta flip this second fraction. Oops, I gotta do it correctly though. There we go. So reciprocal of the second fraction. Now we can take these and factor them. That's a difference of squares, x plus 5x minus 5. That's an easy case trinomial. Numbers that multiply to negative 20 and add to positive 1 would be positive 5 and negative 4. Another easy case trinomial. Numbers that multiply to a 7 but add, or multiply to a 12 but add to a 7 are 3 and 4. And one more easy case. Numbers that multiply to negative 15 but add to negative 2, negative 5, and positive 3. And now, in multiplication form, factored, I've got common factors there, common factors there, common factors there. Now this x plus 4 and x minus 4, notice this is not a negative trick, right? Both x's have the same sign. So we're simply left with x plus 4 on top, x minus 4 on bottom for a final answer. All right, and the last one here, again, first step will be to rewrite it in multiplication form. So times, and put that up top, and that in the denominator. Now, factoring this, that's really just a GCF. All that's in common there is a C. Factor that out, and C plus 2. There's another difference of squares, so 2 minus C times 2 plus C. This, another easy case. Numbers that multiply to positive 4 but add to negative 4 would be a negative 2 and another negative 2. And there's another GCF of just a C. So there's all the factoring. What do we see? We see a lot of C's, right? We see these factors of C's can cancel out. Now, let's point this out. We've got a C plus 2 here, a 2 plus C here. No negative trick involved. This is just about understanding that 2 plus C, rearranging those terms, would be the same as a positive C plus 2. These factors match as is and can be canceled immediately. Nothing required there, just noticing they are the same. Now, the other thing I see is a 2 minus C here, and whichever one of these you want to pick on, there's a C minus 2 here, positive negative 2, positive negative C. Here's another place for our negative trick. So I'll do it with this one up here, factor out a negative, turns that into negative C plus 2, right? We just turned this into that. Now we've got a positive 2, negative c, matching factors. And that's all the canceling. So up top, that's gone, and that's gone with a negative left over, right? Negative 1. So a negative and that c minus 2 up top. And that's all gone, and just a c plus 1 on bottom. Again, a nicer way to write that is just to actually consider that negative out front. And that would be our final answer.